Good afternoon, everybody. Welcome once again to the Heidelberg Joint Astronomical Colloquium. And we've got a very special guest here today, Daniele Huppenkothen, who's just started a new job as an assistant professor in Amsterdam. And to make the announcement, to introduce Daniele, I asked Gabrielina Momcheva, who is Daniele's host.
Good evening, everyone. Thank you for joining us. It's a pleasure to introduce Daniele Huppenkothen as our speaker today. Daniele got her PhD from University of Amsterdam, which she then followed with a move over to the United States as a Morris Sloan Data Science Fellow at New York University, and then Associate Director for the Dirac Institute at the University of Washington. In 2020, she moved back to Europe as an NWO WISE Fellow and staff researcher at ESRON, and she recently started a position at as a staff at University of Amsterdam. Daniele is also very involved in open source software development. She is the lead developer for Stingray, which is a library for astronomical time series, also Entrify, which is a library for cohort selection for conferences. And she is also one of the lead organizers for Hack the Hackathon, which is an amazing conference series that brings together researchers who study hackathons and researchers who organize them to understand and make these events better. And she's going to bring all of this tonight with her talk, Hacking the Universe.
All right. Thanks, everyone. I'm very excited to be here. I hope you can all hear me. No. Okay. It is on. Yeah. A little bit closer. Like this? Okay. We'll see. If in the back, if I stop being audible, wildly gesticulate, please. Actually, but for that, we need a little bit of light so I can actually see you wildly gesticulating. That's great. Yeah, if you lose audio, just like let me know in some way and we'll make it work. Okay, I'm really excited to be here. Thank you very much for the invitation. As I said to Uwe, the last time I was in, well, actually not the last time I was in Heidelberg for Science, but the first time I was in Heidelberg for Science, I was a high school student, and I did an internship with Jose Crespo at the Max Planck Institute for Nuclear Physics, which sort of, in part, set up this long path that now led me here to give a talk to you. I titled this talk Hacking the Universe, and I hope why will become somewhat clear throughout. Before I start, I'm going to start with a disclaimer because I am at an institute that is currently very concerned with information security. And so I just want to say that there were no crimes committed in the making of this talk. When I talk about hacking, I don't mean the sort of illegal, gaining illegal access to computers. All my access to computers is entirely legal. So what do we mean when we say hacking? Hacking comes from a Middle English word called to chop. And I really like the idea of chopping my research projects up into tiny pieces in order to solve them. And then in computer, in sort of the computer sense, dates back to the 50s when it was initially referred to creative problem solving. And that's kind of the thing we want to do a lot in science. We want to creatively solve our science problems. And then I looked at some other definitions on like dictionaries and stuff, and they talk about sort of to work with something on an intimately technical level, which is also true. Everything that we do is very technical. And then it also means to apply a trick or shortcut or skill or novelty method to something to increase productivity, efficiency, or ease. And that is a lot what we do, I think, in data science. We try to find new ways to do our science better. And so this is why I think a lot of it fits with the spirit of hacking. When I talk about data science, there are many different ways to define data science. And in some different talks, I have an entire slide of like Venn diagrams of different data science definitions. But what I would like you to think about when you think about data science is actually, I want you to think about like an instrument in the same way that the Hubble Space Telescope is an instrument. And I would like you to think about it as an instrument that enables us to find small signals in complex data. That is a lot of what we do with data science. Sometimes the signals are small because our data sets are very, very big and we're looking for needles in haystack. But sometimes the signals are small because the data is also very, very complex. So not everything we do with data science is related to big data in some way. And that is sort of one thing I want you to take out of this talk, because often this narrative for data science is it's all about the big data. But even if you don't have big data, and I never do, I always have frustratingly small data sets, even then you can still do data science. All hope is not lost. So, okay. And when I think about science problems, this is going to get a bit philosophical. If I think about science problems, I often think about them in terms of the complexity of the data and the complexity of the models. And there are many axes you could make, and I picked two that are the most relevant to my research. And so on one end of this axis, actually I have a laser pointer so I can do this like this. On this axis over here are problems where we have more data than physical understanding. So think about, for example, GRBs in the 90s, where people had like lots of them and they didn't even know, are they from the galaxy? Are they from outside the galaxy? Right now, that's also problems like fast radio bursts, for example, and that's one of the problems I'm interested in, where we have lots of data, but we don't actually have a theory that would generate the emission that we see. There are lots of theories, but none can actually generate emission. And then on the other end of that spectrum are problems where we have precise models. So you can write down some physics model that can predict what we see, but very complex data sets. And I think that's where sort of cosmology lives. And a lot of physics, astrophysics lives here in the middle. I suspect some of you might disagree with me on that or argue with me on that. And I would actually like you to. So especially after this talk, please tell me I think you're wrong, because I would love to hear from you. If you've never thought of any of this, you might also say, well, where does my research fit in? I don't know. That's for you to find out. But it can be a useful thing to think about, because it helps you figure out what kind of methods might help you solve the problem that you have. And so this is why I like this kind of thinking. And I'm going to talk about problems today, both on this end and on this end, and I'm going to like leave out some stuff in the middle. Again, if you want to chat with me about where you think your problem might lie, please get in touch. Okay, so I want to talk about three things today. I want to talk about data-driven discovery. I want to talk about how we can make astrophysical models better and faster, and how we have to hack academia to make that work in the first place. And data science as a field is extremely collaborative. And so I want to just highlight all the different people, and there are like some whole teams still on there, and people missing, who have been sort of instrumental in a lot of that work. And some of them in red are students that currently are leading work. And this has, you know, two locals with Eva and Morgan who've been co-organizing some of these things with me as well. So that's the roadmap for today. Let's talk about data-driven discovery. Okay. So I am interested, and have been since my PhD, in magnetars, which are highly magnetized neutron stars. So they are the endpoints of stellar evolution. And magnetars are generally, we think, young neutron stars, but they have an extremely high dipole magnetic field of something like 10 to the 14 Gauss. They're some of the like most magnetic things that we can make in our universe. They have relatively long period for pulsars, so of the order of 1 to 10 seconds. And one reason why we think they're interesting is that we think this enormous magnetic field puts very, very big stresses on the neutron star. And the stress release might be a source of star quakes where the entire star starts oscillating. And that's interesting because that allows us to look inside the neutron star, the same way on Earth, when people study earthquakes, that allows them to study the interior composition of the Earth. And we can't actually like drill into a neutron star, so having any way to look at what the dense matter equation of state is very useful. They radiate, unlike most radio pulsars, they mostly radiate in X-rays. And they show some really interesting phenomenology. So mostly we see them as soft gamma repeaters. And the most interesting or the most sort of spectacular of these are what I'm showing up here. This is an X-ray light curve of about 400 seconds. This here says peak not shown because this peak here is sort of like somewhere up there off sort of the screen. And these are what are called giant flares. This event released something like 10 to the 46 ergs, which is only a few orders of magnitude below a supernova. However, the star survived. There was no explosion, no destructive explosion. And so if you want to get 10 to the 46 ergs of energy out of something that is non-destructive, that is actually really hard to do, but it turns out you can do it with very, very strong magnetic fields. What you can see here in the tail, this sort of oscillations, that's the rotation of the neutron star. And these were sort of, we only have 3 of those. This one here in 2004, the gamma ray or the hard X-rays from it were so energetic that they caused a measurable depression of Earth's magnetic fields. You could measure the impact of this in Earth's magnetosphere. But we only have 3 of those, so we need some more data. And what we also see are what are called these short bursts. These are much shorter. These are of the order of usually 0.1 to 1 second. They're about 8 or 9 orders of magnitude less energetic, which is still really bright. And they also radiate in X-rays, and they arrive in what we call burst storms. So each of these lines here, this is now about 10 minutes. Each of these lines here is one of these bursts. And so they arrive in these burst storms where we see hundreds of them within a few hours or days. Again, completely randomly, we have no way to predict them. Eventually something will do something, and then we'll just like point all of our telescopes at it and look at it. Okay. And so the way we think these are created is by having global reorderings of the star's magnetic field. And the star's magnetic field is frozen into the crust of the neutron star. And if you move the field lines, you drag on the crust, and eventually it might break and slip. And that will create an enormous amount of energy that will form a pair plasma in here that will slowly radiate away its energy. We also think some of the emission might come from magnetospheric reconnection as well. But that's the sort of idea. And this energy release also puts this huge energy into the star, which then gets translated, we think, into oscillations. Before we go more into that, I want to talk to you about a different phenomenon and why will become clear in a second. Fast radio bursts are also extremely energetic, but at the other end of the spectrum. We see them in radio. They were serendipitously discovered in 2007 in Parkes data. And for a long time, nobody knew what they were. For a while, a subset of them, people realized they were made by the microwave at Parkes. But these ones we now know are real. We've seen them with multiple instruments. We've seen the same one with multiple instruments, so we know they're astronomical. We could localize them, and so we now, these are not microwaves. They're short, much shorter. They're now of the order of milliseconds, but extremely bright. And most of them are extragalactic, or almost all of them are extragalactic. They're not from our galaxy. And again, we know that at least some of them must be non-destructive because they repeat. We see bursts from the same source multiple times, and now from some sources we've seen thousands of these. So again, they can't destroy the stars. And so the origin is unknown. There's an entire website that collects theories. There's now over 100 with everything from neutron stars to aliens. You can pick your favorite theory. But magnetars are actually a pretty good contender because you have to get that non-destructive energy from somewhere, and magnetic fields are a good way to get them. And there's at least one smoking gun that says some of them must be caused by magnetars, because we have seen an FRB here in yellow from a galactic magnetar. This is SGR 1935 plus 2154. And then in gray here, this is the light curve with the X-ray telescope integral. And so we saw an X-ray burst at the same time as this fast radio burst from the same position. The caveat here it is a pretty weird magnetar, and it is a pretty weird FRB, so they're not entirely representative of the whole population. But we think at least some FRBs must come from magnetars, and so that makes it interesting to kind of study them together. From the data science perspective, first of all, you might say, well, cool, I have a problem where the phenomenon might be produced by the same source. Great. So studying them together makes sense. From the data science perspective, here's an example. This is a magnetar burst. This is an SGR burst in X-rays. This is an FRB in radios. I look at this and I was like, the data kind of looks the same. And so my idea then is that we can use similar methods to study these different phenomena at the same time. So how do we study them? One thing that people tend to always do, if you give someone a light curve of any form, the first question they will ask is there something in there that's periodic? Because periodic signals usually mean that there's a clock in the system. There's something that varies on a very regular time scale, and that is usually hugely constraining to whatever physics you're looking at, because you have to make something that really varies very regularly. And so it makes sense to look for these oscillations, and we usually relax that a little bit and say they can be quasi-periodic. They don't have to be like actually strictly periodic. And so here's an example from a magnetar burst where people looked for a signal in short bursts, and you can see in red here is their sort of periodic signal that they found. But usually we don't really look at this in the time domain. Usually we look in the Fourier domain. And back when I was a PhD student, I was looking at these signals in Fourier space. So this is now frequency versus power. This is a power spectrum, and where the arrows suggestively point, that is the signal. It doesn't look like much, but it's actually quite significant. And so we found these in burst storms. And the reason why we looked at these in the first place is because we saw several of them in the giant flares. And so you can see this big peak at 625 hertz. That is a quasi-periodic oscillation. There's another one here at around 92 hertz. There's a bunch more in there. And this got people really excited, because if you take those frequencies and you match them up with neutron star oscillation models, you can then see which kind of interior composition matches up with these frequencies. The problem with this is that the models are have a lot of parameters, and so you can find you can match quite a lot of different frequencies. And we don't actually have that many. But this is sort of an ongoing topic of research. It turns out trying to find these, unless they're sort of as clear as here, where you have this giant peak in your power spectrum, it is very, very hard to find these, especially in these short bursts. And I know this because that's the statistics problem that sort of haunted my career. So here's like a note for the junior ones under you. If you're like, oh, I'm going to finish my PhD and maybe I'm going to change and work on something else. I don't know, sometimes these problems come back to haunt you. But it is actually really fun. There's a lot of cool statistics in there. And so what we've done recently is look not at the light curves. Here's another two of these bursts. And these are from SGR in 1935. So the source that also had an FRB. Although those are not the ones that had the FRB. Those are two bursts. And what my collaborator did is he chopped this light curve into little pieces and then made a spectrum for each little piece, because we have both time and wavelength information. And then fit each of these spectra and saw what do the parameters of the spectrum do over time. And in particular of interest is the peak energy of the spectrum. So literally the place where the spectrum peaks in X-rays. And what we found, this is what's plotted down here. This is for this burst 1, is the peak energy as a function of time. And you can see there's some structure in there. And we actually found pretty good evidence that this structure is periodic, or at least quasi-periodic, with a period of about 0.02 seconds. And so And this is really exciting because we think this allows you to probe timescales and the geometry of the magnetosphere. We think those are magnetospheric flux tubes and particles going around these flux tubes. And so this allows you to probe the physics of the magnetosphere for the first time, which we think is really exciting. Why I'm mentioning this here is that this is actually not a Fourier domain model. This is a time domain model. This was sort of a new thing we developed specifically for these kind of bursts, for magnetar bursts, but also for FRBs and for gamma ray bursts and any other type of bursts you want to look for periods in. And that was only really enabled by a sort of statistical method called Gaussian processes. I'm not going to talk about these in detail because if I did, we'd still be here tomorrow. But you're welcome to ask me about this later. And so I meant, before we did this, I meant to look at this for a very long time. But I always thought it was too hard to do on magnetar bursts. And so it's like, well, I'm just gonna do it some other time. And then when I was in Seattle, a very different problem fell into my lap because we had some colleagues who were like, we're trying to figure out what the periods are of asteroids. So we're now in a completely different, away from magnetars. But I had colleagues in Seattle who were working on asteroids, and they had these like very sparse time series. So the points here are what you would see. This is a simulated light curve. And the gray one is the actual underlying light curve of the asteroids. And asteroids show periodic signals because they are illuminated by the sun and they are irregular shapes. So as they turn around their own axis, the surface that's illuminated changes. And so the brightness we see change. And so they are very strictly periodic, at least on the timescales that we look at, with some very complicated shapes. And that turned out to be actually a slightly simpler problem than the magnetar problem, but in terms of the statistics, it was extremely similar. And so we could test a whole bunch of the methods that we were interested in by looking at asteroids, and we could then apply what we've learned there to magnetars. And I have a student who's currently finishing up a paper where he's sort of taking everything we've learned here and applies this to active galactic nuclei to find supermassive binary black holes. And so this is kind of one of my stories around like hacking science, where you take, one problem and you say, okay, well, I can't solve it for this yet, but is there another problem that's maybe simpler that I can use this for? Okay. The key challenge with really finding out what the variability is, what if you want to find quasi-periodic oscillations, you have to know what other variability there is so that we can compare against it and ask, is this quasi-periodic or not? And one of our key challenges is that we don't understand the variability in either soft gamma repeaters or in fast radio bursts. And so what we really need is to figure out how that works, what its properties are, and what produces it. And so this is something I've been working on more recently with a student. There are sort of two approaches that you can take, and we've tried both of them. The first one is what's basically a model where you say this light curve here is just a bunch of these simple shapes on top of each other. And so then if you want to know, if you can then look at sort of the rise time of these and the fall times, and you can compare those to physical models, and that's very convenient. But you kind of have to figure out how many of these have to go in here and where they are and what their properties are. And that's very, very computationally expensive. And so the nice thing about this is it's a classical fitting problem. We know how to do this, and it's also very straightforward to interpret. But you make very strong assumptions about the shape of this, and you also have to expend a lot of computational costs to actually make it work. And we've done this a while ago, both for magnetars and for FRBs. I'm not going to go into detail here today. You're welcome to ask me about that later. What I want to talk about is our second approach that we've been working on, and that uses machine learning, which has the advantage that it's very, very flexible and can learn from data. We have to put in much fewer assumptions, but it also needs a lot of data, and it is very hard to interpret. So none of these are without advantages and drawbacks. And ideally, what I really want to do is do both and compare. I think that would be the best way to go about it. Machine learning for fast radio bursts is not really new. People have been doing this for a while, especially with the first Chime catalog, which was sort of the first big data release, released about 400 FRBs. And what people mainly have been doing is to take overall properties of the burst, so its duration, how bright it is, and so on. And what people really are currently trying to do is to distinguish repeaters from non-repeaters. Because we've seen some FRBs repeat, we have some FRBs not repeat. And the question is, are they the same populations and the non-repeaters are just ones we've not seen repeat yet? Or are they genuinely different populations with maybe different causes, maybe different progenitors, where you genuinely have non-repeating sources and some that are repeating? And what people have found with machine learning is that there does seem to be a difference between the repeaters and non-repeaters. There's sort of first evidence that they might be different, at least in these overall properties, like the duration and which frequencies they emit at and so on. And we thought this is great, but we want to be a bit more ambitious than that. And what we really want to do is not take sort of the overall properties, but we want to take the entire data. So what you're seeing here, I've cut out the axes, but this is time, this is radio frequency, and you can see how your fast radio burst changes both as a function of time and as a function of frequency. And we want to take this whole data and see if the structure of these bursts is different for different, for example, for repeaters and non-repeaters, or for different repeating sources, something like that. The way we have approached this is with a neural network called an autoencoder. And the goal of an autoencoder is to take data and to reconstruct that data that you put in. So what you're trying to do is to get the neural network output to be as close to the picture that or the data that you put in as possible. And what we try to do is we put this through what we call a bottleneck. So a layer where the neural network has to squeeze all the information in your fast radio bursts into a small number of numbers. So like 10 variables. And then it has to be able to reconstruct the entire image from these variables. And the idea is, if you do this well, that these variables should be incredibly informative about the data that you put in and sort of the relevant structure in these. Here you can see an example from a simulated burst. Okay, we learned a bunch of things as part of this project. One thing, it's very, very hard to calibrate this kind of method on real data because you put it into a neural network, stuff comes out, and you have some numbers, and they're like, and now how do I know whether they make sense? And so what my student Dirk Kapper went out and did is he built an entire FRB simulation tool first. So that we could simulate FRBs that look different, because we already know that there are some different types of FRBs. And so, for example, there are single peak bursts that have very broad frequency coverage. There are single peak bursts that have very narrow frequency coverage. There are sort of multi-peak bursts here, for example. There are bursts that are drifting, so you can see this sort of slanty shape. And so we wanted to know, can we actually, for example, separate between those different types of bursts? And for that, we had to know what they were. And so we simulated a whole bunch of data, so we knew what we put in. And then before we actually played around with fancy neural network, we did something much simpler. We did principal component analysis, which is a well-known method of dimensionality reduction. And so you can see here two dimensions in this representation. And each point is a fast radio burst, and the colors describe the different types of shapes we put in. And so I found this very encouraging because the different types of bursts actually end up at different ends of this diagram. And so that's good. That means we're learning something. It doesn't do a good job of separating, like really separating things. And so we thought, well, that's a bit sad. I can already spoil this. The neural network doesn't do either. But this is actually probably a real effect, because if you simulate bursts, there will always, and with a real burst as well, there will always be bursts where you can't tell the overlap between, there's always overlap between different classes of bursts, because there might be a burst where which has two peaks, but the two peaks are very close together, and so they might just look like a single peak burst, stuff like this. So it actually becomes, these bursts that are sort of at the overlap are probably real overlap bursts. Okay. But then we did also look at more complex things. We used these autoencoders. We used a thing called the information ordered bottleneck by our colleagues Matthew Ho and collaborators, and that works really well. These are all examples of the original burst, the reconstructed burst, and the difference. And the autoencoder overall does much better at reconstructing FRBs than PCA does, with fewer components, with fewer numbers that you need for the reconstruction. So there's hopefully more information in there. However, one thing that we found PCA is really great for is for outlier detection. These are now the real FRBs. These are 400 FRBs from Chime. And these outliers here, Dirk built this interactive tool so you could look at them. And what we found was that these outliers are actually due to these artifacts here. These are artifacts during the data processing. And so that's not real physics, but at least we can use something like the simple tool to actually find bad data, for example, or data where the data processing didn't work. And then the last thing that we found while staring a lot of these plots is that somehow all of our representations look like fish. And so now these representation plots are also now called the fish plot in our group, because they all look like fish. But one thing we also realized is that we don't really have enough data to do this. And so we really need some better data. Okay, I want to change gears for a few minutes and go to the very other end of this diagram and talk about some of the places where we have models, but we also have complex data sets. And here I want to talk again still about compact objects, because I like compact objects. I want to talk about black holes. Okay. But in order to do that, we have to talk a little bit about how we do science. This very philosophical talk. What happens in nature is that you have a source that produces light. The light gets recorded by a telescope, and that sort of gives you data, and that we then try to understand what happened in this original thing. So we have to kind of reconstruct this entire process. The way we usually do this is by building some kind of computational model. It can be analytical or numerical of this source and how it emits light. And then we put it into some software where people have figured out what we think the telescope does to the incoming photons. And then we compare this to the actual data that we observe, usually, but not exclusively, with something like Bayesian inference. So where we compare, our data model and the physics model to the actual data to figure out what the parameters are. And then ideally we get science. This works really well, but there's also a whole bunch of cases where, for example, this model is really computationally expensive, and then this process gets really difficult to do. And so one thing that we were wondering about and hoping for is that we could use AI to make that better. And so this is what my student Ben Ricketts has been doing for a particular model for accreting black holes. And for this, we're thinking about the question that we're trying to ask is how does matter fall into a black hole? And what do we learn about strong gravity by observing it? And you can actually learn quite a lot. So here's an X-ray spectrum of an accreting black hole X-ray binary, so with a companion. And the spectrum that you see the spectrum, and then you see this like big component here, that's the accretion disk. You see this other component here, which is this sort of flow very close to the black hole, what we call the corona. And there's actually what's called corona reflection, and that's reflection from the emission produced by the corona off this accretion disk. And this coronal reflection in particular is very much affected by strong gravity by the black hole. And so you can learn, for example, about the mass and the spin of the black hole by modeling this. But we don't just look at the the spectrum, we also look at the time series. So here's a time series of a black hole, and again, a sort of power spectrum, so the Fourier representation. And you can see you have this kind of quasi-periodic oscillation that I was talking about earlier, and a lot of sort of variability at low frequency from stochastic processes in the accretion disk. And so ideally, we want to put those two together. And this is what people do in various different ways. But one thing that we think actually happens is this reflection where you have a black hole and an accretion disk sort of sliced through. And then you have this thing called the corona, where we don't really know where it is yet. But we think it's sort of some of the emission we see directly, and some of the emission gets reflected at different radii in the accretion disk. And when it gets reflected at a different wavelength. And so what that means is we have a time delay between emission at this wavelength and emission at this other wavelength. And so we can look at time lags between those, and those can tell us a lot about the geometry of the system and some of these strong gravity parameters that we care about. There's a model we've been working with called RelTrans by Ingram et al., which basically assumes a spectrum for this inner corona, and then does relativistic ray tracing through the system to figure out what we should observe. And so here's an example. You don't have to understand all of this. And the top part is this is the spectrum, the X-ray spectrum again. And then these are the time lags at two different frequencies. And so what we really want to do is we want to put this on, we really want to fit this to real data. This is a fit to a simulation. But if you try to fit this to real data, this can take weeks to months. It's really hard to do. The model is not slow by cosmological simulation standards, but it is very slow by the standards of wanting to do this with statistics. And so the question is, how can we make this faster? And so what my student Ben Ricketts has been doing is he's taken, this model where we say we have some like black hole and accretion flow parameters. It goes through this relativistic ray tracing model, and you get out the spectra and so on. And what he's been doing is he's been training a neural network on these pairs of parameters and spectra to try and approximate all of the physics that goes on in the numerical model. And this works great with some caveats, but in general, it works great. This model turns out to be super pathological. It was really hard to get it to work in the first place. We had to do some like different things to make it work. In general, if you're interested in doing this, some things you might find helpful. We found that sort of a regular neural network, what's called a feed-forward neural network, no fancy convolutions or anything, worked much better than anything fancier we could do. We actually did principal component decomposition of the spectra we were trying to get out. It turns out if you're trying to emulate sort of 4,000 spectral bins, that's really hard. But those 4,000 spectral bins don't all give you independent information. So what you can actually do is you can do a decomposition of all your spectra into 100 components or so, and that works much better. And people have done that before. But then we also had to build a custom function to actually train that neural network. And we found that if you not train just one neural network, but several, that works much better. You can reduce a bunch of error. And so here's an example of these principal components that we learned. So the spectrum that we get out in the end is just like a linear combination of these components. These are just 5. But what's really cool is that this actually learns physics. This actually learns sort of the physics that we put in. This orange one, for example, learns the coronal, a lot of the coronal emission. This purple one here learns this iron line at 6.4 keV that we care about that comes really from this relativistic reflection. And so this was quite encouraging to see that it actually learns things we care about. And so here is an example of a spectrum. At the top, this is the spectrum, both the original code and the neural network. And you can see they're like almost on top of each other. The bottom is the error, and the error is sort of at the level of sort of 3% or so, which is actually the systematic errors of our current X-ray telescopes. We can't actually do much better than that. So that is all right. We then did inference. Here's an example of a spectrum and sort of posterior draws. This took 10 minutes rather than weeks. We get a pretty nice posteriors. They're currently still a bit biased, but that's a thing in our model that we know where the mistake is, and we're currently retraining to get that bias out. But this paper should probably be on the archive before Christmas. All my students are trying to get their papers finished before Christmas. This is neither like a new idea, or it's at least a fairly recent idea, but again, it's an idea that has found interest and has been used all over astronomy, but also all over science. And so, for example, Kerstin did this for supernova type 1a parameters. There's people doing this for exoplanet atmospheres. So whenever you have this kind of model that's complex, that calculating things will hurt, but aren't at the level of like, I take 3 months to just get one simulation out, that is where this can be quite useful, where this is a good application of machine learning, I think. The other thing we have been thinking about is whether we could just like shortcut all of this and just like use AI to do our inference as a whole. And that is entirely sort of recent field of science, not just in astronomy, called simulation-based inference. That is well worth looking up for certain types of problems. I'm not going to go into a lot of detail here today, but I at least wanted to mention it, where you can use now very efficiently neural networks to try and make your inference process much faster. And in some ways, you can use it in cases where you couldn't do regular Bayesian inference in the first place. And I have a bunch of projects with people in Amsterdam and at CFA at Harvard who are applying this to a bunch of different things. Okay, do I have 5 more minutes? Okay, then I'm gonna like record scratch, talk about something entirely different again. And I want to talk a little bit about this underpinning of what makes all of this possible. Because I started out in an astronomy department as, you know, an astronomy student, and I talked mostly to other astronomers. And then I went from my postdoc, I went to a center for data science. And that was an entirely different environment, because suddenly I didn't just talk to, you know, astronomers, but to computer scientists and to psychologists and sociologists and people from all over the place. And I have found that has been sort of incredibly valuable in a lot of different ways. And so I think it is worth talking about how we can do, especially in data science, make our collaboration better. And so one thing that got me interested in is how do we make these data science collaborations productive and goal-oriented and also equitable? How do we make sure they produce something useful for everyone involved? How do we make sure there's a goal? And how do we make sure that everyone involved feels like they are fully engaged and heard and get something useful out of their collaboration? And one way we've been exploring this a few years ago was a bunch of people got together after a workshop in the US and decided to work out some ideas for what is actually required to make an interdisciplinary collaboration work. And this is sort of the figure that people came up with. One thing that I think it's sort of color-coded by people, data, and technology. And you will notice that like people is sort of the biggest chunk of it. And so if you want to have interdisciplinary projects work, you really have to think about the people and how to collaborate well. The good news is there is a lot of research and studies about this. But sort of one big thing is to speak the same language. And I think that's still one of the hardest in interdisciplinary collaborations, that you have to go and learn each other's language. When I first started working with computer scientists, they kept talking about L2 norms. And I didn't know what an L2 norm was. And I looked it up on Wikipedia and I still didn't understand it. And it took me like a month before I went to my computer science colleague. It's like, can you just explain to me what an L2 norm is? And he looked at me and said, oh yeah, there's no good reason why you would know this. And then the next week he came to me and was like, so what is a galaxy? And I'm like, again, no good reason why you would know the precise definition of a galaxy. And so that sort of taught me that you have to figure out a way to speak the same language. And that means you have to ask a lot of questions, even questions, especially the questions that you feel, oh, if I ask that, maybe that's a stupid question. Ask them. It's really, really important. But yeah, so there are a bunch of ideas that we came up with, and most of them are around making sure that people get out what they want. The core thing we put in the middle here is design projects so that everybody benefits. And this is especially true for collaborations, for example, with computer scientists who don't, usually want to just do your programming for you. They have sort of research projects they want to get out. And one of the challenges is finding the research projects that will sort of really benefit everyone. One thing that we learned is that regular departments are actually not great places for interdisciplinary collaborations because everyone is sort of busy with their own field. And so what you might really want to look for is innovative venues. And so there are a bunch. There's sort of things like summer schools and sort of interdisciplinary summer schools. And on this plot, we put a bunch of what we call hack weeks from different fields. I have been involved in Astro Hack Week, which was here a couple of years ago in Heidelberg, which was really designed as a venue for people to come together and ask each other all of these questions and learn from each other and come up with some of these new projects. So one lesson is, if you don't find one of these venues, create one. It's a lot of work, but it's also a lot of fun. And usually you will find people who have always wanted to do that same thing, who have always wanted to talk to a bunch of statisticians or computer scientists or so on. So you can create that venue. The other thing that we found, and that's something that Eva mentioned in the beginning, is that it is really valuable to work with researchers of human collaboration and learning because they have all the knowledge around how to do this well, and especially how to do this equitable. And this is where this workshop series came from that I've been part of, called Hack the Hackathon, where we've been bringing together people who organize hackathons with people who study hackathons. Before this, I didn't even know there were people who study hackathons, but there's an entire, not big, but there's a research field out there of people who are working on this. And they, for example, do things like study, for example, how women experience hackathons of different types, or how scientific hackathons are different from entrepreneurial hackathons and so on. And you can learn a lot from them. And so there's, I'm just saying there's literature out there from which you can learn for how to do some of these collaborations. Cool. And then the last thing I sort of want to mention is that interdisciplinary collaborations really can have real world impact. So with this Hack the Hackathon group, last year we went to Geneva and we got to model a hackathon for them at the United Nations libraries, which was super fun. And they gave us these like big world problems and said, hack. And we're like, okay, let's go. And one thing that came out of it was actually a paper by some of the people who were there, who wrote a paper. Well, one thing that they asked are like, are hackathons for social good actually useful? Do they do anything? And they wrote this paper where they found that, yes, actually, hackathons do have an impact. And they looked particularly at social good software projects. And here's a plot of like the sort of commits to GitHub repositories created or worked on during these hackathons. And you can see that most of the activity happens really at around the hackathon, but there's this long tail of like over a year where people keep contributing. And so you can see that there's sort of long-term outcomes of these. And I want to leave you with a plot with a sort of illustration I really, really like by the sociologists at the University of Washington. There's been a lot of talk in data science about how classical researchers are T-shaped. So they have like this like very broad knowledge, but very shallow. And then they have one leg where they really have their main knowledge in a certain field, and how that had to change to like pie-shaped researchers, where people had to be both like, very good black hole astronomers and very good machine learning people. And what they suggested that actually possibly that's too simplistic, and what we need in the future are these networks of people who have like all sorts of different shapes, and who all need to sort of work together in order to solve all these big problems. And so with that, I'm going to leave you with my conclusions and end here. Thank you.
Well, thank you very much. That's definitely food for thought. I think this is something which is really a revolution, and I'm sure that we can learn a tremendous lot. So I'm sure there will be questions. I'll start with the hall here, but those online, please type in your questions into the chat. Maybe we start if students have got a question first. I see lots of students here today. I don't see anything right now, but
no questions means you either understood everything or you understood nothing, both of which I find a bit scary.
Okay. I mean, oh, there's one at the front.
Not, I can break the ice. So it's not really a question, but a suggestion regarding your FRB classification project. I don't know. Have you ever looked into what is currently being doing in gravitational wave glitch classification?
Not specifically, no.
Because at the end of the day, glitches are things that happen in a gravitational wave detector.
I see. So not neutron star glitches, but like actual.
No, glitches,
okay.
noise glitches in the detector.
Okay.
Essentially, if you look at the spectrogram, so the exact thing you do with FRBs, we have them in the gravitational wave strain as well.
Yeah.
And people are devoting a lot of effort into classifying them and filtering the real signals out of the glitches, and also classifying glitches individually, because they are often related to one specific noise sources in the detector, so that you can classify them. You can also study the noise.
Yeah.
So I don't know.
Yes.
Maybe
I would love to hack that,
because basically it's just changing the name of what you see.
Yeah.
And the spectrogram is the same, and
that's the cool thing with this stuff. You can like, you're like, oh, the data looks similar. Let's see if that works as well.
In this case, they are exactly equal. I think the frequency band is slightly different, but everything else is there. So if someone has an actual question, I'd be happy to.
So thanks you for your inspiring talk. Indeed, to comment on the comment by Stefano, glitches of gravitational wave detections is also what came to my mind when I saw your fast radio burst example. My question is more on the X-ray binary part. You mentioned that the off-the-shelf loss function did not work here.
Yeah.
Do you know why? And then what you used instead?
Yeah. So for context, for those of you who don't use neural networks all the time or machine learning, the loss function is what you use to compare your neural network output to your original data. So in this case, we have spectra generated by our physics code and spectra generated by the neural network, and we have to compare them to figure out how to improve the neural network, how to train the neural network. And so the reason we needed a custom loss function is because we had these principal components. So our neural network would predict principal components, and then we would expand them out into the spectrum and then compare. And what we found was that we needed to compare the principal components directly to make this work. And what we also found was that we need to weight the loss function by the variance that the component explains. So principal components, the goal is to explain, to build a new basis, a new space in the directions of the largest variance of your data. And so the first component by default, by definition, will have the highest amount of variance explained, and then it goes down from there. But if you say principal component 1 and principal component 100 are like same to the neural network, then, but if it's wrong in principal component 1, it has a much bigger effect on the output spectrum than in principal component 100. And so all we did was we weighted it so that the neural network would actually put more emphasis on getting the first components, right? And it turns out by weighting it by the ratio of the variance explained by the last component dividing it by the variance of the last component, that worked really well.
Okay. I don't see anything online.
There's one.
Oh, we do have one? Ah, we do have a question online. Ah, Subishka. Subishka has a question. I'll just read it out. Thank you for the nice talk. My question might be slightly off topic. Could you please explain why starquake occurs and how they are detected? So it's going,
Oh, yes.
the starquakes.
Yeah, okay, so the starquakes. Yeah, I didn't explain that as well as I should have. Basically, if you have a neutron star, the inner part of it we think is a superfluid of neutrons and possibly hyperons, possibly quarks, we don't really know. And then the outer parts of it is a solid lattice of ions. So it's a solid crust. But it is ionized, and so the magnetic fields are frozen into the crust. They can't just move around. And so if the magnetic fields move, which they do because there is global evolution of the magnetic fields, then the frozen field lines will drag on your solid crust. And they will do that for a while until the force exerted exceeds the breaking strain of the crust. And then what we think happens is that the crust slips. And that's kind of similar to sort of specific types of transverse faults on the Earth, just with, on neutron stars, where like the crust slips against each other. And on the Earth, you generate earthquakes when you do that. On neutron stars, we think that generates starquakes.
Okay.
that-
I hope that's
I hope that's a reasonable.
answered Subishka's question.
May I ask a, let's say, mean general question?
Sure.
If you have a time series that is stochastic, how would you treat that?
If you have a time series that is stochastic,
Yes.
how would I treat it?
Yes.
That depends on what I want from it. What do you want to learn?
Well, that is exactly the question I would also have, I guess. No, I mean, to get more specific, so what I do at LSW on top of the mountain, we look at blazars, and they are variable in all ways, shape, or forms. I mean, there is, so far, I've not seen any regularity in them whatsoever. And usually what you see is the first thing that people do is they take the Fourier spectrum of the long time series and get some kind of colored noise.
Right.
And then I have also seen stuff like, okay, they do maybe not just, let's say, normal Fourier transform, but also maybe use some karma models, whatever that actually is.
Yep.
Or I have even seen recently I saw maybe 1 or 2 papers where they also use some kind of Gaussian processes and whatnot, in order to get kind of a handle on, I guess what they try to find is actually if there is some sort of periodicity in there, or understand what the noise spectrum actually is.
So what I would do is call my collaborators at the University of Leicester, Simon Vaughan, and especially his student, Mehdi Lefkir, who is about to submit, because he's also one of those students who really wants to submit his paper before Christmas. He's just finished a really nice paper where he uses Gaussian processes, but he uses them in a very clever way to actually figure out what the shape of the Fourier spectrum is. So in AGN in general, we mostly look at power laws and bending power laws for the shape of the spectrum. And he's found a very clever way to approximate that with Gaussian processes. Because the problem with Karma models, as you've sort of alluded to, they're very hard to interpret in terms of the physics. The parameters of Karma models have no like easy physical meaning. And so we should chat about this. I can point you in the right direction. He has a code that's already public that you can use to model Blazar time or AGN time series and Blazar time series with Gaussian processes to get physically meaningful parameters out.
Okay, be happy to do so.
Okay. If I may just ask myself a question, you mentioned models and how the simple neural networks would be good for using models to inform these networks and then predict data and sort of basically compress the interface between the models and the data set. Is there any reliable way of using neural networks to compare models? I'd be worried about the information loss in the neural network versus the different informations or possible biased informations coming from the models. Can you test the goodness of a model?
Yeah.
Using this?
Right. So what we're doing here, right, is we're training a neural network to approximate the physics in our physical model. And what comes out is, let's say, for example, a model spectrum that we then compare to our data with the regular statistics procedures, chi-squared fitting or Bayesian inference or whatever you want. The nice part about this, doing it like this, is you're only trying to get as good as the physics that's in your model. You're also never going to be better than it because all the information that it has is that model. However, what's good about it is that you can very precisely estimate how well your neural network is doing, which is pretty rare in applications where you're trying to get out physics. In terms of comparing models, I think so. When you say, for example, I don't know, like this cosmology versus that cosmology, or what kind of model?
Yeah, or maybe you want to do something very simple like test whether you can synthesize stellar spectra in different ways through different
right.
something like this.
So I think yes and no. I think to first order, I would probably train a neural network like we have done here, and then leave the rest to statistics. Because with statistical model comparisons, we get guarantees about when it works and when it doesn't work and how it works and so on, which you don't with the neural networks. That said, I know that, for example, the group in CISA, Roberto Trotta's group, they're looking at some of these model comparisons with neural networks for things like supernova cosmology, and they indeed do these kind of things, and they're using very clever forms of neural networks to do that comparison. So you can do it. Every time you do it, you have to find ways to actually check that your neural network is doing the right thing.
Right.
Because you have much fewer intrinsic guarantees about what comes out.
All right. Well, thank you very much. I don't see any more questions, and we have a very important event coming up, which I'm going to just tell you about now. Maybe Cormac, can you just say something about this now? Wait a minute. So, can you go one more slide on, please?
So for all of the PhD students here, we will have an event. We will meet Daniela to have a chat for about an hour with some beer, radler, and soft drinks. And then afterwards, we'll get some pizza for a working dinner, which is absolutely not a social event for legal reasons. So if you'd like to join even spontaneously, just stick around and we'll be in room 106, just around the corner. So all welcome.
Thanks very much, Cormac, for organizing that. And thank you for the doctoral convention for generous funding of that event. Directly afterwards, we're going to meet for dinner. Everybody, not just PhD students, is very welcome to join us at the Dorschenker, just in the Neunhaumer Marktplatz. And my last statement is the previous slide. Yeah, next week we have a change in the program where Philip Birikadis will be speaking about effect of cosmic rays on galaxy evolution. And of course, Philip is a local speaker, but I think that's going to be extremely interesting as well to gather here tomorrow, next week, and hear that. So it just remains for us to thank Daniela for this very thought-provoking. So you know, I think you hit the nail on the head that this is a rapidly changing sort of environment, intellectual environment that we're living in the world. I mean, one has these revolutions from time to time. Let's see how that goes. In any case, thank you very much indeed for this very interesting talk.